Hello everyone, and welcome to, I think this is Module 4. We're ticking on along, aren't we? Today's lesson is on t-tests, and we will cover independent samples t-tests, paired samples t-tests, and one sample. As always, we've got the lesson objectives and the lesson overview that you're more than welcome to pause the video and read for yourself. I want to go ahead and get into just the meat of the lesson. So let's start off with a question for you to answer. What about effect size and t-tests? Remember, we've talked about the two families of t-tests, of effect size before. So when you think about doing an effect size for a t-test, what family of effect does it belong in, the D or the R? And if you want to, you can pause the video and think about it for a minute. And then I want to remind you what the letters D and R stand for. D is for difference and R is for relationship. And so when you think about a t-test, if you think about D and R, a t-test is going to look at differences between groups. And so if you're looking at differences between groups, that tells you automatically that the effect size that you're looking for is a D-type effect size, correct? If that's what you guessed right. Or if that's what you remembered right. Okay, so why is that even important? Why did I lead off with effect size? Because for anything that we do, if we're going to do a power analysis, if we know the effect size ahead of time, a priori, before we conduct the study, right? Then knowing that information ahead of time makes it easier for us to do our power analysis. And remember, power analysis is important because it tells us how many people we need to collect responses from to achieve a power of at least 0.8. Okay, so let's look at a couple of things. Since we're on this slide and it all kind of hangs together, let's look at when you have a D effect size, what equates to small, medium, and large. So a small effect size would be 0.2, medium 0.5, and large 0.8. And you know, one of the things I haven't said, I think, in any of the other lessons is, well, what do you do about values that fall in between? Well, obviously, if a value is below 0.1, I would say the effect size is pretty negligible. If it's between 0.1 and 0.2, I would probably term it somewhere in the very small effect size range. If it's between 0.2 and 0.5, excuse me, depending on exactly how close it is to one or the other of those values, I would frame it somewhere along the lines of a small to medium effect size. And just be transparent about it and say small effect size is 0.2, medium effect size would be 0.5, the effect size for this study is 0.3, and thus falls between those two values. And if you do something like that, if you frame it like that, then that leaves it to your reader to make their judgment about, where they feel like it is in terms of small and medium. And you've just been real transparent about saying there's a wide range between 0.2 and 0.5, and the effect size for this study falls between those two. And then, of course, the same going from medium to large, 0.5 to 0.8. Okay, but all that to say, the effect size drives how many people you need in your study, right? So if you look at the G-power output that we have here, notice that the effect size that we used for this particular calculation was 0.2. So when you have a 0.2 effect size, a small effect size, of course your usual alpha of 0.05, your usual power of 0.8, then look at the size of the sample that you need. In group 1, you need 394, and in group 2, you need 394. So overall, total, you're going to need 788 people to respond to a survey, when we know that in the past, if this survey was used, the effect size that was typically found for this intervention in a population was a small effect size. So you're going to have to survey a whole lot more people. What your hope is that you find an effect size that's larger, because a larger effect size, i.e. an intervention that has a larger effect in the population, when you're replicating that intervention, then you're going to need a smaller group of people to respond to your survey to be able to have a power of 0.8. Okay, so now let's move to dependent samples t-test. This time we're looking at using effect size DZ, which was determined by plugging some information into the determine screen. Again, the alpha was 0.05, power is 0.8. Total sample size for that one is then 787. So small effect sizes equate to larger sample sizes needed. Did I say that right? Every now and then I say these words and I'm like, did I say the right words in the right order? A small effect size is always going to equate to a larger sample size needed. Okay, let's look at what happens when you increase the effect size. What if you increase it to 0.8, which is large? Well, when you do that, all of a sudden you went from needing 787 to needing 12. So that lets you see immediately the impact that effect size has on the sample that you need. Now, a little hint here though. I can assure you that despite the fact that you may achieve a power of 0.8, publication with a sample size of 12 is always going to be a little challenging. So you really, really do want a larger sample size, simply because it is more acceptable or accepted, or maybe a better way to put it is less problematic with reviewers. So you've got kind of this balance between achieved power and what reviewers are going to say about your work. So always think about that too in terms of setting your effect size, setting your sample size. And I've done that before. I have achieved power and only needed 12 respondents, or I think actually it was 18 or 23, I forget. It was a small number, less than 30. And we doubled the number that we were going to have surveyed. And the justification that we used, which is absolutely on point to do something like this, is I may say that I can achieve power by having 12 people respond. But just because I put out 12 surveys doesn't mean that all 12 people of those, if I do a random sample, right, that all 12 of those randomly selected people are going to respond. So I oversample, considering the fact that I'm probably not going to have anywhere near to a 100% response rate. So think about that too as a justification for increasing your sample size. Power's achieved at 12 respondents, but considering the random sample that we were going to draw and the expected response rate, we decided to set our target sample size at X, whatever it is that you set it at. So sometimes you may know that, in this population, I'm only going to get a 20% response rate. So 20% of, let's say, 80 people would be what, 16 respondents? So think along those lines of how many people can you expect will respond out of a randomly selected population, and adjust for that too. Don't just sample or survey to exactly the number you're needing just because, you may not get but 2 responses out of a random sample if you only sent out 12 surveys. So all that to say, there's a lot of options around actually setting your final sample size, and power is one of the things that will drive that decision. Okay, this last one is looking at the question of, if you have a correlation, so an R value, right? Can you enter that correlation coefficient directly into the effect size box for the power analysis? Well, actually no. We need to take that R and transform it to a D value of effect size, right? And so here you've got the formula for transforming R to D. Or likewise, if you have D and what you need is R, you can transform back the other way from D to R. So a little bit of math available for you if you need that for future studies. If you're doing an independent samples t-test, you do have some assumptions that you need to consider. For instance, you need a normally distributed sampling distribution. If you are using a dependent samples t-test, the sampling distribution of the difference between the scores needs to be normally distributed. You need data that are measured at the interval level. And additionally, for an independent samples t-test, the variances, your homogeneity of variance test needs to be approximately equal or not significant. A significant homogeneity of variance test would tell you that the variances are not equal. So that's not good. And you need to have, for independent samples t-test, reminder that we're talking about that one, you need scores that are independent, meaning they are from different people. So contrast that with paired samples t-test, where you've got 2 scores for an individual on each line. So if there are five of us in the room, each of the 5 of us will take the pre-test and have a score, and the post-test and take the score and have a score. Those scores are not independent of each other. Pre-test and post-test are not independent. That's why they're called dependent samples, right? But on an independent samples t-test, you want to only have 1 response per person. Okay, so I mentioned earlier the 3 types of t-tests: independent samples, paired samples, and 1 sample. So let's talk about some study objectives that would go along with each of these, keeping in mind as we go through this that you will need to write study objectives. All right, so an example, IQ scores for boys and girls. Are there differences on the IQ scores between the boys and girls? Are there differences on satisfaction scores with the Tiger Stadium between football fans and the football team? So what I want you to begin wrapping your mind around is that your dependent variable in the first example is IQ score, and your independent variable is gender. In the second one, your dependent variable is satisfaction scores with Tiger Stadium. Your independent variable is the LSU football fans and the LSU football team. So the 2 groups, the 2 football fan groups, I guess you'd say. In the third one, do differences exist between the change in scores from pre-test to post-test for schools A and school B? Now this one could almost be tricky. So make sure that you notice what makes this independent. What happened was you took pre-test and post-test, subtracted those 2 values. Actually, you took post-test minus pre-test, right? You subtracted pre-test from post-test and you got a change value. And then what you did was you took that change value and you had two schools, school A and school B, independent scores, right? And you want to know if there was a difference in the change for school A versus school B. So it is independent scores from those two schools that are being compared for the difference. Contrast that with, in a paired samples t-test, you would have just the question of, is the change from pre to post significant or statistically significant? And if you want to go back to that example, had the question just been, was the change in knowledge from pre-test to post-test statistically significant? Well then, and obviously we're not saying what kind of knowledge change. So a lot of variables that are unexplained there, right? But set that aside and just think, okay, the change from pre to post, was that significant? That is paired samples t-test. But when you take that change and you compare two schools, that's independent samples. Okay, so back to paired samples. To determine if a difference exists in married couples' scores on happiness. Now that's a good one. Why is that a paired samples t-test? Does anyone know? Ideas? Because there's dependence in a married couple. Just like there would be in pre-test and post-test, this married couple represents dependent scores. So paired samples t-test is appropriate in that instance. To determine if differences exist between pre-test and post-test scores for fourth graders taught you using Eureka Math. Again, pre-test, post-test. Pre-test, post-test is just your classic use of a paired samples t-test. When you have married couples, that's a little bit different and somewhere where you have to kind of think outside the box and maybe even make a note to remember that you're going to use paired samples t-test. Can you think of another instance similar to this when you would use paired samples t-test? If you thought of twins and their scores on some construct, then that is another good example. So if you have scores on happiness for twins, would be dependent. Okay, one sample t-test. So this is a question of, you have ACT scores for the population of the US and you have ACT scores for Louisiana high schools. The question is there a difference between the sample mean for Louisiana and the population mean for US? The next example, to determine if differences exist between Louisiana voters' dissatisfaction with the voting experience and national voter dissatisfaction with the voting experience. So again, your population, national voters, and your sample, Louisiana voters. So one sample t-test. That one's actually pretty fun when you've got a big national data set and you can pull out your state data and you can compare your state response data to that national data set to see if there are differences. That's kind of fun. And you see that a lot, particularly in nutrition studies where they have the big, like the NHANES studies. Lots of options for that kind of work when you've got big national studies that are conducted. Okay, so we're going to look at using SPSS to conduct analyses. So one of the things you want to be sure that you do is just look at the means for each of your groups. So here in this example, and I'll go ahead and point out, this says pre-test scores because on the next slide, when we actually do some analysis, it's using post-test scores. So notice that this says pre-test right here, okay? That's important information to have. And then notice that they're telling you what the mean is for males and females, standard deviation, and the number. So those are the three pieces of information that when you're reporting any kind of independent samples t-test, you want to be sure that that's just basic information that you report. Okay, but then they did an independent samples t-test using males and females, but instead of using pre-test scores, we've got post-test scores that were used to do the analysis. All right, so that explains then the difference in the means and standard deviations that you see there in that statistics, that first statistics table. All right, then the next thing you need to do is look to see, are variances equal? Remember I talked about homogeneity of variance was important? This is where it comes into play. So look right here. And what you see is that there is a significant difference. See where it says Levine's test for equality of variances. You've got your F. Oh, I was pointing at the wrong place. Actually, you've got your F and you've got your significance, and it is not significant. So that tells you that your variances are equal. And then you move down here to your t-test. It throws me a little off when I'm turning around and looking at it that way, so I apologize for the confusion. All right, so variances are equal. You're going to use this first line of information, equal variances assumed. And you're going to look down here and you're going to see, okay, it is significant. So that difference in the mean between males and females, where females had a mean of 0.66 and males had a mean of 0.6, that is statistically significant difference between those two scores. So then you're going to report. Variances were assumed equal. Give the F value, give the significance. Then you're going to also go on to report your T value, the degrees of freedom, 198, your significance, P equals 0.03. And then we'll talk about it a little later in a few more slides, but you're also going to report your confidence interval. And you see down there that you've got two, your upper and lower bound of your confidence interval are both negative. Remember, when they're both negative or they're both positive, that would indicate that you've got significance. Don't forget, we talked about it last time. If the confidence interval crosses 0, that would also indicate to you that it was not significant. But that's not what you have here. You have two values that are negative, indicating and supporting the significance level that you have here. Okay, but let's talk about this. When would you use this line that says equal variance is not assumed? So if you had come here to Levine's test and it had in fact been significant, you don't have to throw out your data. You don't have to run another test. Instead, you just say, Levine's test indicated unequal variances, give the F, give the level of significance, and then you come down here and you use this line, and you give the T, and you give the significance value, the degrees of freedom, all of that same information. This is just a more conservative test here at the bottom, when you've got the unequal variances. So use that, had variances been unequal. They weren't, they were equal. But just in case you have a case like that. And you could see that on the test. So prepare. And hopefully some of your assignment will show some unequal variances, and you need to note that. All right, so reading and interpreting the output. Now we're on to dependent samples. So that tells us that we've either got like a married couple's scores that we're comparing, or in this case, we're actually looking at post-test and pre-test. So the post-test mean was 0.63, the pre-test mean was 0.53. Without ever looking at your results, would you anticipate that you were going to have significance? You got a 10-point difference. You might make a hypothesis based just on the means that there would be significance, but you're not going to know until you actually see the test, right? All right, let's move down. You've got the change, well, actually what it is the difference between the pre-test and the post-test. So that change value that we talked about earlier is 0.1, but 0.095 if you're going to not round. So you want to report the change, the standard deviation, the t-value, the degrees of freedom, and the significance. And if you look over there, you see that that 10-point change is highly significant. So P, in this case, because it's 0.000, right, we're going to report it as P is less than 0.001. So remember on the previous slide, remember on this slide, we said P equals 0.03. On this slide, we're going to say P is less than 0.001 when you're writing up your results. All right, and then notice your confidence interval. We're going to swing back around to this in a minute, but notice that both your lower and upper bounds are on the positive side, so that supports your significance, right? Right. And that just tells you that this change mean, the 0.09, is going to fall somewhere between 0.07 and 0.11 with that 95% confidence interval. All right, now we've got the one sample t-test. And what we did here was we took the post-test score for, let's see what group we used, 0.63. So we used the post-test score for this group of 0.63, and we put it against a test value for the population of 0.75. So what you have here is the equivalent of saying, well, nationally, when they do this curriculum, and they do a pre-test and a post-test, nationally, the post-test mean is typically 0.75. It is on average 0.75. The national mean is 0.75. So several different ways you could say that. In our group, the post-test score was lower. It was 0.63. Our question is our group's post-test mean score of 0.63 significantly different from the national average of 0.75? So the difference between those two numbers is 11.9 points. We've got our t-value, negative 9.71, our degrees of freedom, 209. And the answer to that question, is there a statistically significant difference between our post-test group and the national mean of 0.75, would be yes. There is a statistically significant difference. In fact, it's highly significant. P is less than 0.001. Again, look at your confidence interval. You see you've got two negative values telling you that this mean is going to fall somewhere. And if you drew 100 means, 95% of the time they're going to fall between these two values, right? All right, so there's your confidence interval for your mean. And just to review, you're always going to report those confidence interval values along with all the other information that we talked about. So, independent samples t-test, let's review. What are you going to report? You're going to report how many males, what was their mean, what was the standard deviation. How many females, what was their mean, what was the standard deviation. You're going to tell how much of a difference, what was the change score or the difference between the means of the two groups. And then you're going to report the F value and the significance for Levine's homogeneity of variance. Then you will report the appropriate t-value, degrees of freedom, significance, and confidence interval for the test. And I say the appropriate one because remember it depends on, was homogeneity of variance significant or not? In this case it was not, so we're going to report that first line. Dependent samples, again, You're going to report the mean for pre-test, the mean for post-test. The N shouldn't be different, right? Because these are matched. You're not going to use unmatched values. You have to have matched values. This test is useless to you if you have unmatched data. So match your pre and your post. That is, for Melissa Cater, you want Melissa Cater's pre and Melissa Cater's post. You don't want Melissa Cater's pre and John Doe's post. That's unmatched. You'd have to throw both of those out. So N's going to be the same. So report the N overall is 210. Report the standard deviation for both of those means. Then move down here, tell what the difference between pre and post was, the standard deviation, the t-value, the degrees of freedom, the p-value less than 0.001, and the 95% confidence interval. Notice I kind of have an order to the way I'm telling you all of this. You need to do it the same way and report means, mean and standard deviation for the difference, t-value, degrees of freedom, significance, and then 95% confidence interval. Okay, so again, confidence intervals for your one sample t-test also. And then, should you need to compute an effect size post hoc, I have put in a website that you can use. Let's just click on it right quick and see if it will work and see what kind of information you need to have to be able to do that computation of effect size. All right, so there are 3 different calculators here. You've got the one that you use for an independent samples t-test. So computing the effect size for independent samples, again, this is post hoc, right? You've already conducted your study. So you've got information from the study that you just conducted. Independent samples is your first one. Uh-oh, you're not seeing that on the screen. Hold on. Let me see why you're not seeing that. There you go. All right, now you can see it. All right, so when you get to this website, the first one is for the independent samples t-test. All right, the next one, oh, and let's clarify. This one is for an independent samples t-test where you have equal groups. So let's say you surveyed a group of 100 people and you have 50 people in each group, 50 males, 50 females. There you go. Use this calculator. This one is if you have unequal groups. So see in their example here, group 1 had 34 people in it, N1 was 34, and group 2 had 30 people in it, so an unequal group. And you know the groups that we had in the example in the PowerPoint where we had 110 and 90, this is the one that you would use for that one. They give you the formula, but more importantly, they give you the calculator that you can use to compute that. And then the one toward the bottom, the third one that you have down there, is the calculator that you use for a dependent samples t-test or a paired samples t-test. So if you've got pre and post test scores, you'll use the information generated from the output on that to compute your effect size. All right, that said, at the top of the page, it's going to give you some information about what you need to put in there. So you just need to read through and insert the information that it asks for. All right, so let's get back to the PowerPoint. Okay, good deal. All right, so we've talked about reporting results as we've gone through each of those slides. This is just a summary of that, reminding that you need to report how many people, and if you've got 2 groups, you have to report how many people were in each group. Report what the means were for each group or for the pre and the post test. Report what the standard deviation for the means was. Report your t-value. Report your degrees of freedom. And I don't think I've said this yet in the video, but degrees of freedom is usually presented as subscript information. So that's toward the bottom, subscript information beside the T. So you would have the T, and then you would have your degrees of freedom as a subscript number beside that. Actually, that's probably a little bit backwards for you, but your T, and then to the right of that would be the subscript for degrees of freedom. Give your p-value, give your confidence interval, and give your effect size. And then here's an example of all of that information put into a paragraph. There's also a reference for D, which comes out of Cohen's book from 1988. You may or you may not have found it yet, but we did upload the handout as a resource that has all the different effect sizes and what is small, medium, and large for each of those. So go find that. I can't remember now which page I put it in. I want to think it's probably in Module 2, but I wouldn't 100% say that because I can't remember exactly which module I put it in. Anyway, it is there. There's a resource handout that gives you all of the effect sizes, what's small, medium, and large, gives you the reference for Cohen so that you can use that as a reference for anything that you need to reference. All right, so let me just mention that for the test, one of the things I like to do is to give you a paragraph and ask you what information is missing. So if I ask you what's missing, you're going to read that paragraph and then you want to be able to look at this chart and say, I don't see that she reported the standard deviations for the means. Those are the kinds of mistakes that I might be asking you to look for on a test. All right, so here's some examples of things you could see. If I gave you a screenshot of the power analysis software, do you know which numbers go in which boxes? We talked about that. If I gave you a screenshot, can you tell if the test was adequately powered? So that's just asking you, do you know where the power is at? And can you tell, is it 0.8 or higher, or is it less than 0.8? So that's what that question is asking you. Do you know where to find the power denotation on that screenshot? Can you recognize the assumptions for independent and or dependent samples t-tests? So for example, the question of homogeneity of variance. If I gave you a study objective, can you determine which t-test to use? So that's simple. Just put down 3 examples that were on those 3 different slides and quiz yourself. Can you recognize which t-test to use for each of those objectives? And remember the example about the schools. I showed you an example of it being independent, and then I verbally gave you an example of it being dependent. So that's another way to quiz yourself to see if you know how to do that. Could you write a study objective for independent paired samples or one sample t-test? Again, following the examples that you have. And when you write a study objective for the test, I am looking for you to do it in the same manner that we talked about in the previous slides, or in the previous lessons, that is, where you're using information from your study. So use examples from your study when you write these study objectives. And if I gave you SPSS output, can you interpret the results? And let me give you some examples of the kinds of questions I might ask. So I might ask you, was homogeneity of variance test indicating that variances were equal or unequal? Was the t-test for the independent samples t-test, what was the degrees of freedom? Or was that a statistically significant test or not? So those are some examples of questions I would ask you. Could you report what the confidence intervals were for the t-test? Do you know what those numbers represent? Remember the lower bound and the upper bound that the mean's going to fall between? So in 95, if you had 100 change scores and you pulled them all out, 95% of those scores are going to fall between the lower bound and the upper bound on the confidence interval. Do you know what family of effect size is appropriate for a t-test? D, right? Given the output from an effect size calculator, can you interpret the effect size? So if I gave you an effect size of 0.5 and I told you that it was a D type effect, you would tell me, oh yeah, that's a medium effect size. So that's what that question is asking. Can you report the results of a comparison of means? I think that should say on a t-test. Yes, you could. So it's just asking you, can you write a report? Using that list of items to include, can you write a report? Yes, you could. If I gave you a report, can you tell me what's missing? And I'll tell you, that's my favorite kind of thing to ask. And if I gave you 4 different reporting examples, can you identify elements of the analysis that should be reported but that were missing from the report? So those are all examples of things that you would see on the test. All right, and so that brings us to the end of Lesson 4, Module 4, t-tests. Next week we will go on to, I think it's ANOVA and repeated measures ANOVA. So looking forward to seeing you. As always, if you have questions, hit me with an email. Look at the question and answer forum. Probably email's the better way right now because I'm not seeing a lot of other things come through. Okay, thanks, and talk to y'all soon.